All right. All right, last lecture. As you can tell, I'm worse. So if I have to cough or more importantly, blow my nose in the microphone, I do apologise. Okay. Last thing. This is going to be the easiest thing we've done in the whole unit, believe it or not. All right? Once we get through some terminology, of course. So as I said, we've done two types of first order differential equations. There are a couple of other different types that have solution strategies that work, but you'll learn if you're doing math. If you're doing a math degree, and in second year you do Introduction to Applied Maths, that's basically an entire unit on differential equations. So it's a very rich, very broad area. But we're going to move on to second order. And the fascinating thing I find about, because I solve differential equations a lot, is everything you learn in first order doesn't work at second and higher. Everything you learn at second and higher are general methods, but as we'll see, they are very restrictive. There are very few second and higher order differential equations that we can systematically solve. They are very complicated, and that's what people like me spend most of our time doing, is coming up with new ways to solve new types of second and higher order differential equations. But in general, just like a first order differential equation can be written in the form, the first derivative is some function of x and y, and you're looking for the function y. The most general form of a second order differential equation is where the second derivative is a function of x, y, and y's first derivative. And the aim of the game is to find a function y that works. However, writing in this form, there are basically no solution strategies. None. There's nothing separable or things like that. And it actually, there's lots of reasons, but one of the reasons is, remember that we often think of the first derivative, dy dx, as a fraction, dy divided by dx. And that I've said several times that we can't do that with higher order derivatives. You do not think of the second derivative as a fraction. You can't. It doesn't make sense. It actually doesn't make sense for the first derivative, but we do it because it works. Right? It does make sense in one way, but we just do it. But we can't do it with second order. So one of the reasons is we can't play games and move things around. Right? So the most general form of a second order DE is this, but we have almost no chance of solving it. Right? So now we stick to linear first. Right, so a second order linear differential equation. Remember here, linear means linear in the unknown function y, what you're looking for, not x. Doesn't matter what x is doing. Right, but the general form of a linear one is where it's a linear function in the where the second derivative is a linear function of the first derivative and y. So just like a linear first order DE was, remember dy dx plus some function of x times y equals some other function of x. The general form of a second order linear is the second derivative plus some function of x times the first derivative plus some other function of x times y equals some other function of x. We still can't solve this. Right? We can only solve this with two specific cases. They're constant coefficient, which is the one we're going to do, and Cauchy-Euler, which we're not going to do. Right? Right, but this is a linear one, where here p, q and g are arbitrary functions of x. Some terminology. A second order differential equation is said to be homogeneous or homogeneous, depending on how you want to pronounce it, if the right-hand side is 0. They're the only ones we're going to look at. Otherwise, the differential equation is called non-homogeneous, and this g function on the right-hand side is called the non-homogeneous term. Right? Solving non-homogeneous ones requires a lot more work, right? And it involves things that we call particular solutions and general solutions, not something we're going to do in first year. Right? But even if it's homogeneous, so if we've got this and the right-hand side equals 0, we still can't solve it for general P and Q. Right? We can only do it if P is, oddly enough, 1 on x, and q is 1 on x squared, or if p and q are constants. That's the only case we can do. Right? We're going to look at the case where they're constants. Right? And this is as simple as it gets. Right? So in the case that the two things out the front are not functions, but they're constants, and we've got a homogeneous one, then we have a second order linear homogeneous differential equation with constant coefficients. And that's the only one we're going to be able to solve. And it's only the one of two that we can actually solve with a general strategy. I'll show you I'll mention the other one in a moment. Right? So that's the one we're going to tackle. Right? So given a question, it'll turn out that the way to solve it is all we have to do is solve a quadratic. That's it. That's all we have to do. Right? Since two integrations are required, however, just like with a first order DE, there's one arbitrary constant floating around. For a second order DE, there are two that we call C1 and C2. You can call them whatever you like. I just call them C1 and C2. Right? The two different integration constants. One comes from integrating one, because formally, to solve this formally, you have to undo the second derivative. You've got to integrate twice, so there's two constants. Right? And we usually call them C1 and C2. Now, the principle of superposition states that if we have two functions that are both solutions of the differential equation, of the linear differential equation, then so is this combination. Right? So let's say we've got some function y1 that's a solution and another one y2 that's a solution, then a constant times y1 plus some other constant times y2 is also a solution because it's linear. Right? That's proved in the unit reader. It's very straightforward. Right? But I can't claim that to be the general solution yet. Remember, what I'm looking for is the general solution, a solution that covers all possibilities. Right? I can only claim that that's the general solution if these two solutions, y1 and y2, both satisfy the differential equation and are what we call linearly independent. In other words, in function terms, they are totally different functions. Now, if you've done linear algebra, if you've done Math 101-2, you will have done lots of linear dependence and independence already with vectors, yeah? With vectors of constants. Here, we're just doing it the same thing with functions. In other words, what it's saying is these two functions are fundamentally different functions. One is not a constant multiple of the other. So if one solution was x and another one you find is 2x, they're not linearly independent because one is 2 times the other. But if you found one was x and the other one was x squared, that's good. Right? We have a simple test to determine if two functions are linearly independent. We calculate something called the Wronskian, right? Which is basically, it's a 2 by 2 matrix where the first row is the solutions, the second row is their derivatives, right? So, and it's the determinant. So top left times bottom right minus top right times bottom left, right? It turns out if the Wronskian will either be always 0, so identically 0, or never 0. Right? It may turn out that sometimes it is 0, but when you go on and do more in differential equations, it'll turn out those values of x where it is 0 won't be allowed. Think of it like this. Say you've got a differential equation, you find the solution is y equals 1 on x. Then automatically x equals 0 isn't allowed, right? Because you can't evaluate it there. The solution doesn't exist there. So it might turn out if you were doing one with the Wronskian would be 0 at x equals 0, but that won't matter because the solution doesn't work there anyway. You see? So for us, either the Wronskian's 0, which means we can't build the general solution, or it's not 0, which means we can. Right? So that's just some terminology. Now, to prove all of this, you need Math 101-2, and I know some people have done it, not everyone has, so take my frickin' word for it. All right? When you go on in second year, especially if you're doing maths, you'll do an entire unit on differential equations. You'll do things like existence and uniqueness theorems and more on the Wronskian, and this guy's name will pop up a lot, Abel. He did a lot of work on differential equation. He also found a differential equation called Abel's differential equation, which is the bane of all applied mathematicians because it can't be solved. And it pops up all the frickin' time, all the time. Anyway, that's something you'll learn about later on. What's the conclusion? Here's what we're doing. Given a second order linear homogeneous differential equation. We are only going to do the case where P and Q are constants, but this is true if P and Q are arbitrary functions of x. So a second order differential equation written in that form. The general solution is C1 times one solution plus C2 times another solution, right? And there are your two arbitrary constants. And that is the general solution provided those two functions are linearly independent. Well, that is, when you find their Wronskian, it is not identically zero. Right? If it is identically zero, we don't have the general solution. That's all we need to know. All well and good. How do we find these damn things, these two solutions, y1 and y2? Well, first off, let's have a look at some special cases. Let's say, for example, we had that, right? And I need to find, let's make life easy, let's just find a solution first. All right, how would I do it? Well, look at it. I need a function whose, when I find its second derivative and add 2 times its first derivative plus add itself, I get 0. In other words, I need a function whose derivative is proportional to itself. And there's only one function that does that, the exponential function. It must be an exponential. It can't be anything else. It turns out it can be something else, but we'll get to that in a minute. Right? For the moment, the exponential is the only thing that'll work, won't it? Right? So it's logical to try exponential functions. E to the mx and see what happens. Right? And just see what happens. If you plug that in, you'll get that. Right? Because if I differentiate e to the mx, I get m e to the mx. Differentiate that again, I get m squared e. M is a constant I'm looking for. Now, of course, since the exponential function can never be 0, I can divide it out. It's never 0. All right? Quadratic. And that'll give me my value or values of m. Notice this one only gives you 1 because that's m equals minus 1. It's only one, the only solution. All right? Now, the only other type of differential equation, there's only 2 types of second order DEs we can solve this way, right? That we actually have a systematic method. This is one, and you see it's obvious why they've got to be exponentials, isn't it? Because that's the only function whose derivative is proportional to itself. Nothing else will work. Right? I mean, there might be products of polynomials and exponentials or trigs and exponentials, right? But exponentials have got to be in there somewhere for this to work. There's only one other type we can do. Imagine if we had, this is not one we're going to look at. This is called a Cauchy-Euler differential equation, named after 2 mathematicians, Cauchy and Euler, obviously. Now, look at this one. Now, what do I need? Look at it carefully. Notice that the power of x matches the derivative, doesn't it? X squared times the second derivative, x times the first derivative, x to the 0 times y itself. So the only thing that could possibly work is x to the n, isn't it? Right? Because then this first term would be, you'd have an x, this would be x to the n. The derivative x to the n minus 1 times x becomes x to the n. This is x to the n minus 2 plus 2. Right? And they're the only 2 we can do. Right? If this was, say, that, can't do it. Right? And to solve that one, that would be, I have no idea. right? But you do a series, you do Taylor series, Taylor polynomial solutions when you're stuck. That's what we do, right? We call them power series solutions, something you'll learn about later on. But the key thing is that second order, there's only, remember first order we did separable and linear, two totally different types of differential equations and two totally different solution strategies. When we get to second order, we're very restricted to what we can do without resorting to very advanced mathematics. I mean, one of the coolest things I learned, there's a couple of things in my math, when I did my math degree that I learned that blew me away, right? And one of them is called perturbation theory. That's a method of approximately solving differential equations. Another one's called the calculus of variations, which is how you do things, answer questions like, why is the soap bubble round? Right? You can prove that mathematically using something called calculus of variations. But the absolute coolest thing I learned was a general method to solve these differential equations by change of variables called Lie symmetry analysis. Right? And it was amazing, but I learnt it in honours. Right? It's not something you can handle at undergrad level because you need a lot of background to get it to work. Right? But my point is that differential equations will, solving them, being able to solve them generally is a skill that comes with years of practice. And it's a skill that people like me in research still develop. Right? So differential equations are really difficult things to solve. But we're going to look at the simplest case, right, which is the constant coefficient. So as I just explained, this is the only one we're going to do. Right? So if P and Q are constants, we see that logically an exponential's got to be involved. It can't be anything else. Right? There might be products with exponentials, but the exponential's got to be in there somewhere. So the logical thing to try is a solution e to the mx, and we look for m. Right? Plug that in, and take out the common factor e to the mx, because that's the whole point of the x. Every time you differentiate it, it comes back in its original form. That's the point. Right, so when you get down to it, because e to the mx can never be 0, the only time e to the x is 0 is when x goes to minus infinity. Of course, this is not an equation we're solving for x, this is an equation we've got to solve for m. Right, and of course m is minus infinity, that's stupid, we don't want that one. So we can divide out the e to the mx and we've basically got m squared plus pm plus q, a quadratic. Right? And notice that it's like replacing the second derivative with m squared, the first derivative with m and y with 1. You see how it comes almost immediately from here. You just identify P and Q, solve that. That's it. All right? So this quadratic is called the characteristic equation. And if you had a cubic with constant coefficients, you'd have a cubic characteristic equation. Right? If you had an order 38 polynomial, you'd have a differential equation that's linear, you'd have an order 38 polynomial you've got to solve, which, fingers crossed, would spit out 38 distinct roots, right? Which probably won't happen, but it might. Right? But this idea extends to higher order. Now, of course, being a quadratic, we know how to solve a quadratic. I would frickin' hope so at this stage. Right? We know that we can solve a quadratic. Right? And we also know that we're only interested in, usually we're only interested in real things, but we all know that a quadratic has two real roots, one real root, or two complex roots, don't we? Right? We all know that. Right? So it's going to split into cases depending on what's going on. Right? So if we have two real distinct roots, say m1 and m2, we are done. Right? We've got e to the m1x is one solution, and e to the m2x is another. We can calculate their Wronskian and notice that it is never 0. Right? It's not identically 0. That means that they are literally independent. Therefore, I can claim that that is the general solution. A constant times e to the m1x plus a constant times e to the m2x. Done. Right? Couldn't be easier. What about if they're complex roots? Well, we know also that when they do appear as complex roots, they are complex conjugates of each other. So remember, if one's 1 plus 2i, the other root would be 1 minus 2i. That's a consequence of the fundamental theorem of algebra. Right? But let's say we get two complex roots, right? Well, then we've got exponentials with a complex number in them, which we don't want. We have a differential equation with real coefficients. We want our solution to have real things in it. Right? But we can use Euler's famous formula. Everyone should have seen Euler's famous formula, e to the I. Usually it's e to the I theta equals cos theta plus I sine theta. Anyone not heard of that? Right? The most famous formula in mathematics, because it's the most famous because if you plug in theta is pi, you get what's generally regarded as the most beautiful formula in all of mathematics, right? Because it involves all the important constants, e, I, pi, 1 and 0, right? And it is called and it is a beautiful thing to behold if you're a mathematician. Don't laugh, right? It really is. It's an amazing thing, right? To really appreciate it though, you do need to have a good firm grasp of complex functions. That's again something you'll learn about later on in engineering or maths. But anyway. But playing around with Euler's formula, we're never going to have to do this again. All of the summary of all this is going to be written on the formula sheet. All right, but you can play around with it a bit and get down to here, right? That C1 e to the a no, don't do that. I must see its slideshow, sorry. C e to the ax times cos of bx plus an e to the ax times sine of bx, where your roots are a plus or minus ib. So a is the real bit, b is the imaginary bit of the roots of your characteristic equation. Right, so not exponentials are involved, right, but there's some causes and sines there. And this isn't probably that surprising either. If you've got a second order there, we started by looking at this and saying, well, I need a function that when I differentiate it, I keep getting it back. Yeah? Well, of course, trig functions kind of do that, right? But you have to differentiate it twice. You differentiate sine twice, you get sine back again, don't you? Differentiate cos twice, you get cos back again. So it's not really a massive surprise that sines and coses have appeared, right? And of course, they're mixed in with exponentials. Right? And if you calculate the Wronskian, same deal. It's not identically zero. I can claim this is the general solution. What about the final case? Equal roots or a repeated root, right? Like the example I did on the thing, m squared plus 2m plus 1, that's got a root m equals minus 1. Well, in that case, you get one solution, right? Because your quadratic only has one solution. You get e to the mx. What the hell is the other one? Right? It doesn't tell you anything. Right? You don't have any more information. You know you need a second one, and it's got to be linearly independent, but you can't find it. Here we use a technique called reduction of order, right? And I'm going to show you the gist of it. What basically happens is we know we've got half the answer. Reduction of order lets us get the other half, the half we're missing, right? What we do is we start with what we know. We know that y1 is a solution. Let's imagine our second solution is some other function times y1, right? And here I've called it v. And if you plug that into your differential equation and do a hell of a lot of algebra, you will eventually get down to that v's got to be a linear function in x, right? So my solution is v times my first answer, which was e to the mx. So I get e to the mx plus x e to the mx. So in other words, this process is telling you that when you've got a repeated root and you only get one solution, your second one is x times your first one. Okay? So this is a process called reduction of order, right? And although you might wonder why, we didn't reduce the order of anything, right? When you do this for a general, because what often happens is you might have some, especially when you've got non-constant coefficient ones. Let's say you've got some, right, it turns out P and Q are not constant. So usually that means we're screwed, right? But sometimes you can look at it and say, oh, but I can see that x is a solution, right? By pure chance, x is a solution. Y equals x works, right? But I can't pick the other one. Sometimes you could pick one by inspection, right? But you can't pick the other one. And it'll turn out what often happens if one's x, the other one's like frickin' log of x plus x squared plus 3x squared, plus, you know, God knows what the hell it is, right? But we need a process to do it. And what we do, let's say we can see by inspection that that is a solution. I then assume that the general solution is an unknown function v times the solution I know. And what is guaranteed to happen is that this thing will become a second order, what appears to be a second order differential equation in V. Right? But it's guaranteed not to have a V term. Right? It's not magic, but it disappears. Right? And so when you think, well, so frickin' what? I started with a second order, now I've got a worse one. Not necessarily. If you let W, bear with me, if you let W be the first derivative, this actually is a first order DE, which we have an army of techniques to solve. Right? Hence the term reduction of order. Right? You have to solve a first order DE. Right? Hence reduction of order. That's what this technique's called. Okay? Very cool technique, but very tedious algebra-wise. Right? So what normally happens is when you get to here, you'd have a plus something times dv dx. It turns out in this simple case that's 0 as well, so I can integrate it immediately. All right? But anyway, and we find that a second solution in this case is x. So if one solution is e to the mx, where m is your single root from your quadratic, the second one you need is x e to the mx. And I can calculate the Wronskian of these two. I need the product rule for x e to the mx. It's not identically 0, done. Right? Because if the Wronskian is not 0, you can be certain that any other solution is a combination of those two. That's all you need to build the general solution. So, in summary, this is all you have to do. And instead of looking at this, let's look at the formula sheet. All right, so this is easy. This is really, really easy. Right? I'm going to ask you, if I ask you to solve, this is the only type of second order DE I'm going to get you to solve, with constant coefficients. It's got characteristic equation m squared plus pm plus q equals 0. If the quadratic's got two real distinct roots, that's the answer. And this is a formula sheet. How kind am I? If they're complex conjugates, that's the solution. If you get a single repeated root m, that's the solution. Done. That's all you have to do. All right? Easiest thing we do in the whole unit. All right? A lot of background theory and stuff that I've glossed over, but that's all you've got to do. Okay? So, find the general solution of this. Characteristic equation, you can almost do it without thinking. Well, the characteristic m squared plus 3m minus 4. Right? It is important to understand that it comes from assuming a solution of the form e to the mx, but I'm never going to get you to redo all this Wronskian stuff again. You just take my word for it. Right, so all you've got to do is solve a quadratic. Well, this one's easy to solve. Can I think of two things that multiply to give minus 4 and add to give 3? Hopefully the answer is yes. 4 and minus 1, so the roots are minus 4 and 1. Bang, that's the answer. Done. That's all you've got to do. Easy. M squared plus 2m plus 1. Right? M equals minus 1. Done. Right? Straight off the formula sheet. M squared plus 4m plus 20. Remember how we solve quadratics? You go through a process. First off, can I think of two things that multiply to give 20 and add to give 4? No. Doesn't mean there aren't two numbers, it just means you can't think of them, right? So quadratic formula, right? And turns out they're complex, right? Real part -2, imaginary part 4, right? Look at the formula sheet, right? We've got -2 plus or minus 4i, replace a with -2, b is 4, done. Right? That's all you've got to do. Right? Now, when this unit was, when we used to teach for 13 weeks, we'd do non-homogeneous DEs. That would be the last topic. Right? Obviously, this is the last, I haven't got time to do it. So if you do look at past, or you get that book of problems from the math union or whatever, we're not going to be doing non-homogeneous ones. This is all I want you to do for second order. Easy, yeah? Something nice, easy to end on. All right, what I'm going to do this afternoon is I will upload some information about your final exam and the final exam from last semester, which is what we will discuss in the last lecture. So we won't cover any material in the last lecture, we'll just chat. Right? So make sure you do have a look at both and read them and come with any questions. All right? Okay, I'll see everyone then.